Okay, yeah, so I think we can get started. So thanks everyone for joining. Today it's my pleasure to introduce Jeevana Inala, who's currently a senior researcher in the deep learning team at Microsoft Research. And before that, she completed her PhD at MIT with Armando. And she's worked on a variety of topics, including program synthesis, neurosymbolic learning, and currently on AI for code. So yeah, thanks for joining us today, Jeevana, and I'll let you take over.
Yeah, thank you, Osbert, and thanks for inviting me here. And thanks for the great introduction. So I'm actually really very excited to be here to present some of our new stuffs that I've been doing at Microsoft Research on program synthesis using large language models combined with some symbolic reasoning. So a year ago, so most of my works focused on replacing large neural networks with neurosymbolic models, which is a combination of programs and small continuous models. And the main motivation for doing this is that we can achieve better generalization, interpretability, and data efficiency in some domains such as robotics. But then in the past year, there has been tremendous improvements in large language models and their applications in writing code. For example, we have this OpenAI's Codex model, which is built on top of GPT-3 and trained on a lot of GitHub code. And it showed great promise in writing code, and it's even deployed within VS Code as the GitHub Copilot extension. And then we have a model from Google, AlphaCode from DeepMind, there's Polycoder from CMU, and so on. So there's basically like one model coming up every 2 weeks. And I'm actually truly impressed by these models' ability to generate code in general purpose programming languages such as Python. I mean, earlier we were all doing very domain specific languages in the program synthesis applications. But these models are able to generate like Python code, C++ code, and so on. And they have great ability to understand natural language. And in most cases, they are actually able to generate the correct code when given multiple trials. So inspired by the success of these large language models, most of my current research is about how can we improve these large language models for code using symbolic techniques while still retaining their benefits. And in this talk, I will mostly present two approaches we took to achieve this goal. The first one is using fault-aware neural code rankers to prune out incorrect code during inference time. And the second approach is to use program execution to learn from semantically equivalent programs during training. And these are actually very fresh works, which we plan to put on archive soon. I actually think the second one should already be on archive as of yesterday. So first, I'll start with fault-aware neural code rankers. And by the way, feel free to interrupt me in between and ask questions. I do have a lot of hidden slides that I plan to bring it up if there are questions related to that. So this work is it's joint work with several of my colleagues from Microsoft Research who are working in this area of AI for code. So the task here is we are given a natural language description of the desired function, and we want the model to generate code such that when we run this code on the set of unit tests that are given as part of the task, we want the code to pass all these unit tests. And this task is actually taken from a public data set called apps. So if you look at some of the existing code generation models performance on this data set, so we see that if the model is only allowed one trial, which is the pass at one column, then it achieves a very low performance. But if the model is allowed to take 100 samples and we only check if any one of these 100 samples is correct, then it achieves a better performance. So for example, for the Codex model, it goes from 3.8 pass at one performance to 24% pass at 100 performance. So a key question here is how can we bridge this gap between pass at one and pass at 100? And many of the existing approaches, like I think AlphaCode, the approach that they take is to filter these samples from the model by executing them on some of the unit tests that are given as part of the task description. However, there are several issues with actually executing code at inference time. So first of all, even if the code passes the few given unit tests, it could still fail on the hidden test or on the unknown unit test. And then there is extra burden on users to provide unit tests for each task. AlphaCode actually alleviates this issue a little by also automatically generating the test inputs, but there's still other issues, like you need to install the dependencies for the project, and there could be incomplete code if your project is under development. And another issue is that some of the code generated by model could actually do potentially unsafe operations like deleting files from the disk. And so you need like a sandbox mechanism to safely execute these code. So all of these issues make it hard to do execution-based filtering during inference time. So this leads us to neural rankers, where the idea is that we feed the task description together with the sample program to a model, and then the model predicts whether this code is correct or wrong without doing any execution. And then we can use this model's predicted probability as a score for ranking the sample programs. But instead of just making the model predict a single binary label correct or wrong, we can actually do more. So actually, if you take a code and execute it on the test, the compiler output that you get actually tells us exactly how this code failed. So for example, in this program, the compiler output throws a type error because this program calls random.choice on an integer, but the compiler is actually expecting a sequence, like a list or something like that. So. And here is another example where the sample program from the model produced the string output, but the expected output is actually an integer. So the key intuition of our work is that a neural network trained to distinguish between these various failure modes can actually have a better understanding of the program and the task, and hence can do better at ranking programs. So in our approach, we actually have a hierarchy of labels for each sample program. So at the highest level, we have the two binary labels, correct or wrong. And then we split the wrong category into either execution errors, so these are compile errors or runtime errors, and intent errors, and these are code that actually executes, but it produces the wrong output. It does not produce the desired output. And each of these classes themselves have further subclasses. So for example, under execution errors, we have subclasses such as type errors that we saw before, or there could be a name error, index error, timeout exception, and so on. So we actually derived, like, I think 10 classes by parsing the compiler output on these codes. And similarly, for the intent error, there are different types, like the outputs could be totally of different types, or they could be arrays of different lengths, or one of the outputs could be none. So again, we actually came up with these subclasses manually by inspecting several outputs from the training data set. And finally, for the execution errors, we also know the line number that resulted in the error. So that's also one of the labels here. So we create this fault-aware ranker dataset with these fine-grained labels. And to get the different correct and wrong programs, we actually use these 4 different code generation models. to sample 100 programs for each task in the app's training dataset. And then we execute them to create 4 different datasets, one for each model. So here in this plot, we can see the statistics about these datasets. So we can see the number of correct code and the number of codes that result in execution errors, number of programs that result in intent errors. So a couple of things to see here are, so if you actually, so along the x-axis, you actually see that the model size is decreasing. And then as the model size decreases, we also see that the number of correct programs is also decreasing, which is expected. But we also see that the number of execution errors keep increasing as the model size decreases. Okay, so, and then once we have this fault-aware ranker dataset, now we can train our rankers to solve a variety of tasks of various granularity levels. So first we have this baseline binary ranker that is trained to just predict whether a program is correct or wrong. And then there's a ternary ranker, which is trained to predict between correct, execution error, or an intent error classes. And then there's an intent error aware task, which expands the subcategory, which makes the model learn the subcategories of the intent errors. And similarly, for the execution error aware task, the model also tries to predict the exact type of the execution error. And then finally, there is one task where we try to make the model learn both the execution error types as well as the error line number. So we actually designed these tasks so that we can understand how does training on easier versus harder classification tasks might impact the ranking performance. And to implement these ranker models, we used CodeBird as the base model. So CodeBird, for people who don't know, is a BERT-style model. It's a code understanding model that is trained on the Code SearchNet dataset. And on top of this CodeBird model, we added a classification head and then a line prediction head. And then we fine-tuned the weights by training on these ranker datasets. So any questions before we look into some of the results?
Wait, sorry, where did the unit tests come from? So you still have to get unit tests for this, right?
Yeah, so our data set is created on this apps, based on this apps data set, which comes with a set of unit tests. So it comes with a prompt, and then we use the model to generate candidate programs. And each prompt also comes with unit tests, and then we use these unit tests to execute and get the labels.
I see. So the benefit compared to alpha code, or the kind of, but yeah, the benefit compared to something like alpha coder is that you have the more fine-grained output labels. Is that right? Or...
So alpha code actually filters out program by executing it directly at inference time. So here we are kind of
during test time. Oh, sorry, training time.
Training time, yeah.
Oh,
so
I see. Okay.
It's not even training time. It's only during the dataset creation time.
I see. Okay.
So we just use execution for creating the dataset, and then we train the models and then use that to replace execution during test time.
Okay, yeah, got it. Thanks.
Any other questions? Okay, so let's look at some of the results now. So the first result is that rankers actually improve code generation performance. So here, the blue line shows the Parset1 performance of various code generation models on the apps dataset. So for people who don't know what Parset1 means, so if you sample one solution from the model, we check whether that solution is correct or not with respect to the unit test. And then Parset1 measures the fraction of such correct code. So the blue line is the baseline without any ranker. So this is just the base model. And then the orange line shows the results with the ranker. So basically, we take 100 solutions from the model. We rank them using the probability determined by the ranker, probability that the code is correct, as determined by the ranker, and then we take the top solution and see if that's correct or not. And so if you do this is ranked facet 1. If we do that, we can actually see that we can get a significant improvement in the performance. So, and basically higher numbers are better here.
Which ranker is this? Because I guess you had many, right?
Right. So this one is the best ranker out
Okay.
of all the 5. Right, so I'll show the results on the ablation a little bit later. So yeah, so basically for every model, we took the best ranker. So what this result shows is that rankers actually improve code generation performance of actually all models irrespective of the sizes. So we have models ranging from 125 million model to 6 billion, and Codex, we actually don't know the size because they don't reveal it. It could be either 12 billion or I don't know, 175 billion, I think. So another interesting thing to note here is like if you take a GPT Neo 125 million model and you combine it with a ranker, which is also another 125 million model, you get a performance that's similar to GPT-J, which is like 50 times, which has like 50 times more parameters. So that kind of shows like how much rankers can help.
I have a question. So when you write pass at 1, that means just taking a single sample, or is there still some kind of beam search decoding going on and choosing the highest likelihood according to some number of samples?
So this is just taking a single sample.
So how would it compare to, did you do a comparison to doing some kind of beam decoding?
Not beam decoding, but we tried to play with different temperatures. So if you use a lower temperature, your facet 1 number would increase, but your facet 100 would decrease.
Right. Yeah, but then you're still doing greedy decoding to get, or not.
Yeah, if you use temperature 0, then you get the best solution.
Is that always the case? Even if because I thought if you do beam, you need to do some kind of beam search to get the best solution, because even if you kind of decode greedily, you can, make some choices that look good early on.
Oh, okay, yeah. So temperature 0 would give you the greedily best
right
solution.
So it seems like you still need to do a comparison to some kind of beam search then, because effectively you're kind of giving it the multiple chances here.
Yeah, but yeah, so that would increase the facet 1, but it also changes the distribution of your 100 solutions. So it could also change the rank facet 1 value. So this one is this one is showing that, okay, instead of taking a random sample from your 100 solutions, if you just take like, if you rank them and then take the solution, then you get this much bump.
Sure.
Right? So the distribution changes, so the results would change too.
Yeah.
So yeah, I don't think I have the results on the temperature ablation here, but it's in the paper. So once it's on archive, we can see it. Yeah.
Did you say how big the ranking model was relative to some of the models?
It's a 125 million model. It's CodeBird.
I see.
I think it's 120. Yeah, it's like one of the smallest models here. So that was on the validation set, and these are on the test set. So on the apps test set, these are actually significantly harder set of problems than the validation set, and so the values are kind of smaller in scale than the previous slide, but we can still see like a significant improvement. And I'm also showing the facet 100 numbers here as a reference, because that also is the upper limit for what the ranker can give us. So an interesting thing that we found is that the rankers are actually transferable to like a different code generation data set without any further training. So when we evaluate it on human eval, which is the data set introduced by the Codex paper, we can see that the performance improves from like 26% to 32%. And similarly on MEPP, which is another data set introduced by the Google's large language model for program synthesis paper. And even here, we can see an improvement from 36% to like about 42%. And this is the ablation on the different ranker tasks that we train. So there are 4 training curves, one for each model. And each curve, the y-axis is the ranked pass at 1 on the validation set. And the x-axis is the training step. And higher values are better here. So on the top row, we have Codex and GPT-J, somewhat bigger models. And here we see that the orange line, which is the ranker trained on the ternary task, is the best. On the bottom row, we have GPT-Neo 1.3 billion and GPT-Neo 125 million models. And these are smaller models. And here the data set is much more imbalanced with like a lot of wrong code. And on these models, we see that I think in this case, it's the ranker trained on intent-aware task. And in this case, it's the ranker that's trained on both execution-aware plus error line prediction that does the best. So here, I mean, it's not a big sample to make any substantial claims, but it kind of seems like if you have smaller size models where the data has more wrong code, these harder training tasks access better regularizers. And the blue line is the baseline binary task, which you can see it performs worse than many of the fault-aware tasks. And this is okay, so these are similar training curves, but instead of measuring the ranked pass at 1, we measure the fraction of tasks where the topmost code executes but without any errors. So we call it exec at 1. So here you can see that the green line and then the purple line, which are trained on fine-grained execution-based labels, which are trained to distinguish the execution error labels, they perform best. And the binary task and the intent-aware task are actually the worst, the blue and the red lines. Okay, so to summarize this, yeah.
Could you comment on why the lines are downward sloping for the purple and the green line?
So I think they are overfitting.
Right, that's right.
So this is like on the training set. So initially it learns to actually figure out all code that produce execution errors, and then it overfits a little bit.
And this is on the testing set, what you're plotting here.
This is on the validation set, yeah.
On the validation set.
Yeah.
Thanks.
So we mostly care about pass it once, so that's why we let the training go on, because these numbers are kind of increasing. Any other questions?
Right, so the accuracy for these tasks is pretty high, right? I mean, it seems like.
So this is only checking if the code executes. So that's high, that's like close to 80%. Yeah.
Yeah.
The best one is close to 80%. So
yeah, that still seems pretty good. Is that
so this is only, yeah. So this is only checking if the code does not have any syntax or runtime errors. So this one is the actual accuracy, which is lower.
Oh, and what is and this is for like what kind of error happens? Is that the difference, or?
So this is, you want to get code that does not have errors, but also produces the right output. Does not have execution errors, but also produces the right output.
Got it.
Okay, so to summarize this part of the work, so here we propose to use fault-aware neural rankers to rank sample programs from a code generation model, and our fault-aware rankers, they're trained to predict fine-grained classes of failure modes, and we show that it improves performance. It improves pass-at-1 performance for various code generation models on various data sets. Okay, so yeah.
So I was wondering if you compare with using like a type checker as a ranker, like pick the first one that doesn't have any type errors.
Oh, we didn't. Yeah, that's actually a good question. Yeah. We didn't because we want to totally avoid any kind of, I don't know if, I think they also need to have dependencies installed properly, right? Or
Right, yeah, like right thing is like we're using Python or something, yeah.
yeah, so we want to totally avoid any kind of heavyweight stuff.
Okay,
So yeah, but that's an interesting comparison actually. Yeah.
thanks.
I had a quick question. So, have you looked at, let's say, when you try the parse it 100, when you sample it 100 times, is there any observed similarity between the samples that do get generated, in the sense that the likelihood of finding like a solution is much higher, but then amongst the different samples that do get generated, among the 100 samples that do get picked up, is there seemingly a tendency to sort of converge towards like the right solution?
Okay, so I'm not sure I totally understand the question, but so first of all, like all 100 solutions are almost always different.
Right, but how different are they is the question that I'm asking, in the sense that are they unique enough, or are they still sort of in the same ballpark trying to get to the same correct solution, whichever manages to pass the test case? So if I were to do like a k-means between the 100 solutions, would they actually cluster to something which looks similar?
I'm not sure. I haven't done that except like manually looking at some of these solutions, and they do look different even for the same problem. But there are also like some tasks for which out of the 100 solution, like 80 of them are correct.
I see.
But there are some tasks where for out of 100, only like 1 or 2 of them are correct.
I see. Because why I'm asking is seemingly, I mean, parse it 1 is the metric that you want to go after, rather than parse it n, because that's what is desirable probably from like a product standpoint.
Okay, so we also have parse it 5 metric.
Right. Okay.
But which we show in the paper. I just removed them for
sure. But yeah, if parse it 1 is like from a product standpoint we want to go after, then probably sampling 100 times, and if there's some means to find like a right cluster at least, then that could be like an interesting way to prompt it to users and get people to fix things after having localized the structure at least.
Yeah.
Right. Thanks.
Yeah. So it actually started off as thinking about from VS Code perspective, right? So we don't want to show 100 solutions to the user. We can only show like 1 or 2 of them.
Right. Got it. Yep.
When you're using it as part of the Copilot system, right?
Yep.
So. All right. So are there any other questions or?
So this is maybe a little bit more of a philosophical question. So what is it that makes it easier once you have a full piece of code to tell whether it's wrong or not, given the specification, as opposed to like, why can't that information just be internalized by the network that is trying to produce the code? Why should we expect this to work?
So I think it's, in some sense, it's the regressive nature of these the large language models, the way they generate. They don't get to, you don't get to see what you're generating afterwards, right? But I think if you look at the full code, it's kind of easier to see like how, like why there are errors there. But I also think it's probably maybe because I mean, in some of these could be made part of the training as well. Like you could make the large language models, like during the training, you could improve it. So that's probably the next part of the talk, and also some of the future work that we want to explore. Because I've seen some cases where the model just uses like totally wrong variable that's like not declared before. I think those should be possible to also instill during just the large language model training part. But I also think it's the way that these large language models are trained, because they don't get to see wrong code. They just see like all the right code, and they have to just make assumptions that, okay, this is the right way to do things. So if they're also trained on trying to know more about like, okay, this is a wrong code. Maybe they will avoid some of these errors too. So I don't know, does that answer your question, Armando?
Yeah, I think all of these things make sense.
Mhm.
So partly I think it's the incremental nature with which the model is outputting code that it never gets the big picture of and it's harder for it to backtrack once it does the wrong thing. And also I guess you are using more data for this model than what was used for the original model.
Right,
So
right.
you also have all these wrong examples.
Mhm. Yeah. So yeah, actually that's a little bit of that is what I will talk about in the next part of this talk. But also we are planning to explore more about that direction, like how do we improve training itself. Okay, so let's keep going and then I can take more questions later. So in the previous work, we saw how symbolic approaches can improve code generation and inference time. But in this work now, we also explored a way to improve code generation during training time by learning from self-sample correct and partially correct programs. So this work is primarily done by our intern Anne Song Ni, together with several people at MSR and Ale. So the task that we consider here is a math reasoning task. It's similar to the task before. There's a natural language prompt describing a math problem. And we want the model to output a program that solves this math problem. And one issue with most of the existing data sets is that they only have like one goal program for each task. And then they train models on these data sets using a supervised learning approach. But usually there are multiple other semantically equivalent programs that also evaluate to the same desired answer. So you don't have to read into these codes, but they're different and they actually evaluate to the same correct output. So one of the drawbacks from just learning from one single goal program in a supervised fashion is that the learned model becomes overly confident in its predictions, even if it's the wrong prediction. And there is usually less diversity in the sample programs. So in this work, we want to explore learning from multiple semantically equivalent programs. Now, how do we get these additional equivalent programs? So one approach is to manually collect additional goal programs, but that's a very expensive process. So we take this other approach of sampling these additional programs from the model itself. So our algorithm is fairly simple. It starts by keeping a buffer of correct programs for each task. And this buffer is initiated with just the goal program in the beginning. And then at every training step for each task, we sample a set of K programs from the model learned so far. And then we filter out programs that do not compute the correct answer. We know what's the correct answer because we have the goal program here. And then we filter out all duplicate programs, and then we add the rest to the buffer. And then when we learn, we actually learn from all these programs in the buffer. So this was our straightforward algorithm for learning from self-sampled programs. So sometimes it's hard to sample fully correct programs from the model, but if you look at many of the sampled programs, they're almost correct. And so we want to leverage them also during the learning process. So for example, here is a fully correct goal program. Again, don't read too much into the code. But here is a sample program that is actually correct up to line 5, but it's also different from the goal program if you only consider the first 5 lines. So we want to also make use of this partially correct program during learning. And we know that this is a partially correct program because if we look at the execution trace, so after 5 lines, the second program produces a state that is exactly the same as one of the states produced when you trace the goal program. So it's shown in the red, solid red boxes in this picture here. So this means that it's actually possible to complete this partial program in a way that we can go to the desired output from this red state, because we know that the goal program did it. And once we find those partially correct programs, we just add them to the buffer from before and make the model learn from both partially correct programs and also fully correct programs. So one thing that we assume in this work is that we only have straight line programs, which is the case for this math reasoning task, which also makes this execution-based tracing a bit easy. And we actually leave exploring execution-based tracing for programs with loops and branches for future work, which should also be interesting. Okay, so
wait, sorry, could I ask a quick question? So, I mean, this works if like there's a correspondence in the variable, you know, like a one-to-one correspondence in the variables in the first and second program, right? But like what happens if you just have like a different way of computing the output? Is that going to kind of be marked as incorrect, even if it could?
Right, so we have okay, so our definition is that we need to have the same execution state, and a state is defined as just a set of values that the program computed so far. So it is a little bit invariant to variable names and all.
Right.
Variable names and orderings and all. But as you said, it could be possible that you don't actually need those 26 to compute the final answer, but we kind of emphasize that you need 26 when we say that the program is correct. So it is a little bit conservative. Yeah, so that's also probably one of the future directions to make this definition less conservative. Yeah.
Okay, so and is this imposed for all programs? Because you could just generate a program that produces the correct answer using a completely different approach. So would you still rule that out, or is that then okay?
Oh, so if you get the correct answer, then we keep it.
Even if it's generating it using a different strategy?
Yeah, even if it's generating using totally different trace. Right? So if it generates the correct answer, we keep it. But if it does not generate a correct answer, we check if any of the states matches any of the state from a known correct program. Okay. Not just the goal program, but any of the known correct programs in the buffer.
Got it. Thanks.
Yeah. So the next problem we have here is to figure out what loss function to use when you have multiple goal programs, multiple targets. So first of all, when there's only one target, the go to loss function is just MLE, maximum likelihood estimation, which just computes the negative log likelihood estimate. But when there are multiple targets, we have different options. So one of the options is to just sum the loss from the multiple programs in the buffer. So you just sum the log likelihood. So this is similar to just treating the sample programs as just any other data points in the data set. So it's kind of like data augmentation. And another option, which was explored in this previous work, is MML, maximal marginal likelihood. What this does is it first marginalizes the probability over all programs in the buffer, and then takes the negative logarithm of this probability. So they kind of look similar, but if you actually look at the gradients, they are very different, which affects the learning process in different ways. And one key thing that we noticed is that for the MML case, the gradient is actually proportional to the likelihood of the sample itself, which makes the model prefer to learn from the most likely correct program rather than all the programs in the buffer. And we found that this has same issues as learning from MLE with a single target. So I'll show more results later, but a sneak view is that MML does not do so well. MLE aug is the best loss function. And in the paper, we also have another loss function called beta MML that acts as an intermediate between these two losses. Okay, so let's look at the results. Here is our experiment setup. So we evaluate on 2 publicly available data sets, grade school math from OpenAI and math QA data set. So we actually realized that the original data set has a lot of duplicates across training, validation, and test sets with only like small numerical changes. So we created a filtered version of this data set after removing all such duplicates, and we evaluate on that. And we use 2 different models, GPT-Neo 125 million, GPT-Neo 2.7 billion, to analyze the impact on model size as well. And for the metrics, we use Facet K for different K values. Right, so here is the first result. This shows that learning from sampled programs help. So here we have 1 plot for each combination of data set and model, and solid bars are for our approach, and dashed bars are for the baseline that doesn't do any self-sampling. And we can see that our approach improves performance, but you can see most of the improvements on Facet K for higher K values. There is really not much improvement on Facet 1, except for this one case on Math QA with a bigger model. And this is expected because our approach is mainly focused on improving the diversity of the multiple samples. So it makes sense that it improves Facet K for higher K values than the lower values. So then we also study the impact of partial programs. So here you can see 3 bars. The blue one is MLE, that is without any self-sampling. Orange one is our full approach that uses both fully correct programs and partially correct programs. And the gray one is without partially correct programs. So the gray one is the ablation. So you can see that even if you don't include partial programs, we still get a good performance over MLE. But if you actually include partial programs, you get a further bump in the performance. And actually, if you actually also look at the number of programs found in the buffer, so if you use both fully correct programs and partially correct programs, you get almost twice as many programs on average per task in the buffer than if you ignore partially correct programs. So we also found an instance where partial programs does not help. So this is on Math QA Python dataset with a small model. And here, actually, if you don't use partial programs, it's slightly better. We don't have a great explanation for this, but it seems like with a small model in this data set, the model is not really able to find any partial programs, not really able to find many partial programs. So here you can see that this orange bar is kind of much smaller than in the previous case. So it's probably not helping much. Right, and finally, if you compare the different loss functions, as I mentioned before, MLE-OG is the best. It beats MLE that doesn't use any self-sampled programs, but MML actually makes it worse. And we also found if you use MML with partial programs, it makes it even worse. So MLE-OG is the best loss function, and beta MML, as I mentioned before, is like an intermediate between these 2 loss functions. Okay, so to summarize this part, so we augment the learning approach by self-sampling additional correct and partially correct programs. And the results show that self-sampling improves Facet K for higher K values, and partial programs help in most cases, and MLE-OG loss is best for handling multiple targets. So are there any questions here?
I guess I have a bit of a general question. Is this approach, because I mean, you've been looking at this Math QA benchmark, but does it kind of apply to a more traditional, did you look at a more traditional like synthesis benchmark, like the ones that you were looking at in the first part? Because it's still a problem there. Because there are multiple.
So we could, okay, so we don't fully know how to do partial correctness for a general purpose program. I mean, we have some ideas how to deal with loops and conditionals, but that requires a little bit more brainstorming. But we could do, if we don't have partial programs, we could do this even for apps kind of benchmark. We didn't do it. It's like, yeah.
Okay. But it's something that you could in principle try, and you just have.
Right. So this also has this problem that you're still doing execution during training, which is better than doing execution at inference, but you still have to do this complicated execution during training.
Right.
So, yeah. Okay. So we are actually even like trying to see if we can combine both of these approaches together. Like, can you use the neural proxy for execution as part of here during training, and see if that helps. So that's like actually our next summer project that Theo is going to be working on. I think Theo is in the audience here. Yeah.
I guess I was also, so I mean, you could also imagine solving this. So you've been using this kind of handcrafted supervised learning approach, but you could also imagine trying to solve it using reinforcement learning, right? Is that something you considered, or?
I think there are parallels between reinforcement learning and this one. I mean, it is kind of reinforcement learning combined with imitation learning, some on-policy sampling and all, right? So I think the loss function is also different if you compare to reinforcement learning, which is these loss functions that we used. So there was a prior paper. So this paper compares reinforcement learning to MML, and they say MML does better than reinforcement learning.
I see.
And
yeah, I wouldn't be surprised, because
right.
you know, reinforcement learning doesn't usually work that well.
Right. So, yeah.
But here, I think you can interpret this algorithm as RL. We have a very, very similar paper actually that is up on archive a month or two ago.
Yeah, I would love to look at it too. Yeah.
It's called STAR, Self-Taught Reasoner, and in there we analyze this as a kind of certain reinforcement learning objective. We also thought that MML was going to work better, and it didn't, and we didn't include it in the paper actually because it just didn't.
Okay, so you found reinforcement learning was better?
I mean, I hate to say it like that because that's never true, but like for this particular problem, doing the the thing that looks like reinforcement learning seems to be better. In particular, like treating them independently and doing an argmax for the decoding was a lot better for the last step, was a lot better than doing the more like sampley things.
Okay.
Yeah.
Yeah, I'll take a look at the paper. It should be interesting. Yeah. What kind of domains do you do? Like, I'm just curious.
So we also do GSM 8K, but the main domains are like a super simple toy arithmetic one, and then we do common sense QA, which is our kind of main target.
Okay.
I mean, it's cool that the same thing works for common sense QA because there are no programs. You can't actually validate whether the reasoning is correct or not. But the self-generated reasoning still helps a lot in improving the model.
I see. Yeah, that's interesting. Yeah.
We also do it in a few shot, so we don't actually have any examples of reasoning in the training data. We do a few shot prompting, and then the fine tuning is purely based on self-generated things. I'm not sure if it's an important difference or not. Probably not.
Yeah, I mean, so we have a requirement that we need the gold program here, mainly for this partial correctness check. But we also tried without the gold program, and we found that it's really hard for the model to sample by itself like a good correct program. These are like long programs requiring like long chains of reasoning steps. So we found that the gold program actually helps us with like avoiding like a cold start.
It might be very interesting to compare these because we don't assume we have a gold program.
Yeah.
We're doing, very much weekly supervised.
Yeah.
And it does bootstrap over time to get better.
Right.
We also learn from incorrect programs part of the time, Anyway, yeah, it's cool.
And I think even without the gold program, we also ran into spurious programs. like
Mhm.
programs that would just like output the answer without any reasoning.
Mhm.
The
Mhm.
gold program also acts as like a regularizer against that.
Yeah, that makes sense.
Yeah.
In terms of implementation, sampling is really expensive, right? So how do you just kind of like have two phases where you sample a lot and then train for a while, or how did you do that?
So we actually sample only one program in the buffer for every training step. So I said sample K programs, but the K is just one because it is expensive. And we only also sample only for the batch, tasks in the batch.
I see. So for every
So-
batch, you get a bunch of gold standard and then augment it with these self-sampled, and then you
Right.
do just one gradient update, or you train on each batch for a little while.
No, I think it's just one update up, but we should. Yeah, I'll ask my intern too for more detail. I didn't do the implementation, right? Yeah.
Cool.
Yeah, but yeah, it is an expensive training process actually. So compared to MLE, we are getting good performance, but we're also training much longer.
Yeah.
Yeah.
We gave up on doing it per batch, by the way. We sample a big batch by forward sampling, and then we run fine tuning for a while. So it's kind of off policy.
I see. Yeah, we thought of exploring that, but I think it's also because our models are kind of smaller. I don't know what model sizes you were using. So
Yeah, we were using GPT-J, so
okay, yeah, that totally makes sense. Right. Yeah. All right. I think that's mostly all my slides. So overall, we showed some promising approaches to improving code generation using large language models with some neurosymbolic techniques. But I should say that we have not reached 100% performance yet. So there's still a lot to achieve here, and hopefully we'll see a lot more improvements in this area in the upcoming years. So happy to take any more questions that are there.
Yeah, thanks so much for the great talk, Jeevana. And yeah, I think we have a few minutes for questions. I see someone in the audience has Aditya. Do you want to just unmute?
Yeah.
yourself?
Thanks. So this is a general question across the two papers, right? One thing is to use these kinds of proxy signals for correctness, like execution errors or having multiple programs share similar states during execution and so on. There's also a kind of algebraic similarity, which is the reason things are equivalent, which you can capture by using rewrite rules or using some kind of abstract domain or these other things that so in some sense, I mean, the silliest way I can phrase it is maybe the model is kind of forced to predict these abstract states while it's also predicting the program, right? In some sense, so that's kind of keeping track of the execution, roughly speaking.
Right.
Do those approaches fare better, or would you think that fare better? Did you try anything like that? Because those would be more direct signals in my kind of imagined universe.
Yeah, I mean, we didn't do it explicitly, but it came up in a brainstorming about like, okay, maybe we should explore programmatic rewriting rules for finding these other programs, other equivalent programs, rather than by self-sampling. And I mean, it's easy to come up with some of the rules, but it's not always the case, right? Right. So on some harder tasks, that could be like really hard to come up with rules that captures all kinds of equivalences. I think you also bring up kind of like normalizing the program somehow and making the model learn that, right?
Or just using abstract domains, right? Because the rewrite rules can
Right.
be hard. The equivalence checking can be itself a complex problem. You can use abstract domains that will kind of capture several facets of the kinds of values you're manipulating, right? Lengths, whether they attach to the, I don't know, the main memory that you have, or they're dangling or whatever.
Right. So yeah, so we obviously didn't do an experiment, but something that we tried was like that came up that was like if you actually allow the model to, if you restrict the model to just output in certain formats, it's actually making the model worse. But if you give the model more freedom, like if it could like output comments and write random stuff in the comments, it actually makes the model perform better somehow. So I don't know if just restricting the space of language would make the model better.
Oh, sorry, I don't mean like that. I mean in terms of actually feeding it as an additional signal at each step. It's not really an output, but it's more like a just like your neural rankers or whatever. Right? So your ranker is now based on, I don't know, the abstract semantics. Right.
Yeah, so there's also the trend that if you make the model learn more things, it's better as well. Right. So there was Scratchpad paper from Max here was also making the model learn the intermediate steps. So that made the model better at learning to execute. So we kind of seen similar thing with the fault aware paper, where we make the model learn the exact failure more, and then that makes the model better. So there could be that kind of a regularization effect happening too.
All right, thanks.
All right. Any other questions? We have time for maybe one more question. Okay. Yeah, I guess in that case, we can wrap up. Thanks so much for the great talk, Jeevana.
Yeah, thank you all for listening.
Thanks everyone for
Thanks,
coming.
Oscar.
Yeah,
Thank you.
thanks.
Thank you.
Bye.
Bye.
Bye, everyone.